Welcome to the Azure Cosmos DB Essential Series Season 2. My name is Mustafa. I'm a product marketing manager for Cosmos DB, and in this episode, we're going to cover a little bit about data modeling. And when we look at data modeling, specifically, we're going to look at schema design. So before we dive into schema design, let's define schema just to give everyone a refresher. Schema is the structure of how you're going to arrange different properties or columns within an item. And that item could be a document, a vertex, or even a row for all intents and purposes if you're in a relational setting. These are all different ways of combining properties or columns, and what you're going to see when you look at Cosmos DB or other NoSQL databases is that we typically represent relationships slightly different than in a relational context. In a relational database, we have normalized tables and we draw relationships across them. In NoSQL, we do not. So let's dive into an example right away. For this example, we're going to imagine that we are building a database for an insurance claim system. When you normalize the data model, what you typically end up doing is you break up things by entity. So you might have an entity called claims. You might also have a set of entities called the claim line items. And what happens is, as a patient files a claim, that claim might have a bunch of different little line items under it. So using the example, let's just say I tore my ACL. And as part of tearing the ACL, I had to go get both an MRI to get the ACL examined, as well as get ACL reconstruction surgery. Now, when we go and model that in a relational database, you're typically normalizing, where you have a claim that might have metadata. So when we file my claim into the insurance, we'll have diagnosis, insurance, insurer, payer, provider. All of that metadata may be stored in a claim object or even separate in their own independent tables. To simplify, the MRI, the reconstruction surgery, etc., would be rows in a claim line items table, and then these, of course, get joined together from a foreign key, likely the claim ID. So what's the problem with normalization in this context? There's a subtle thing that's happening here, which is by normalizing, we are incidentally optimizing for storage, and there's a hidden penalty for compute. There's no problem until we scale. So from an application point of view, a lot of times if we were to build an application with, let's say, a REST API, as you post these pieces of information into the API, what you're generally doing is on every write, you're shredding the data. So we have to shred that claim and then write multiple entries under the line items table. And then every time I read that data, we have to reassemble everything. So we're going to look at the disk, grab the claim. We're going to go look for the claim line items. And then we're going to do a cross product in the form of a join to join these two pieces of data back together. The challenge with joins is they don't work very well in a transactional scenario that scales out. And so whenever you do a join across multiple nodes, doing the cross product across a node boundary in a sharded architecture tends to have very heavy performance penalties, both in terms of throughput and latency, because the join requires a high degree of node-to-node coordination. And this is exacerbated by the more nodes we have. So instead of joining across the two short database shards or partitions, imagine that if I had 100 database partitions doing joins, it's going to be pretty prohibitive to do that many joins across those partitions. So in summary, at the micro level, normalization is just fine. But once our data set starts to get larger and larger, we start to run into heavy compute challenges working across partitions. So what happens if we denormalize? A common technique to denormalize is to effectively take objects and embed them into another object. And so this is where you take advantage of the type system, where the type system supports nested objects. A less optimal way to denormalize is to nest all of the line items under a single claim document. Now in this case, what I have here is some sample JSON. We're going to use the document-oriented data model just as an example. And what you have here is we have a bunch of claim information for my ACL tear, which we can go and query for by, let's say, the query team. We can look at all of the claims that were filed for between a certain date or for a certain doctor. And alternatively, if we want to, we could also filter on any other field in the metadata. But zoom out and we'll see the challenge here. When you denormalize many items under a parent document or a parent object, what would happen if the number of line items is exceedingly large? Now imagine that instead of having just 2 line items, we have, let's say, many line items, maybe 100,000. In such a case, you might end up running against boundaries for what is the largest record size that can be in your database. So there's actually another approach for denormalizing. Typically, it's pretty intuitive for people to do what we just did, embed children into the parent entities. But what usually yields a better design is to actually do the reverse. Instead of embedding children into the parent record, embed and copy the parent record into the child records. So with this third option, in this case, what we're going to do is we're going to take a document line item, and here I have a document for the ACL reconstruction surgery, as well as a document for the MRI. And because we frequently query off of certain fields in these documents, what we're going to do here is we're actually going to copy the parent object and duplicate it across these other documents. Now, effectively, there's going to be some trade-offs. Engineering is all about navigating the right trade-offs. By duplicating information, I'm now taking a hit on storage. I'm having to store the claim metadata more than once. In fact, I'm going to have to store it based on a multiplier of how many line items I have. But the advantage to this is, for my example workload, if I'm frequently querying for a set of line items one by one over time, I'm adding a line item and adding onto this as the patient makes progress through their treatment plan. Now, what you'll find is that writes can be made very cheap, because rather than having to append an object into this parent array and having to rewrite this entire document, we can go and do tiny, much smaller updates. So in summary, option 1 is normalization, and the trade-off is between compute and storage. Option 2 is denormalization by nesting a child in a parent object, which becomes a trade-off between storage and write throughput. Option 3 becomes a sacrifice on storage at the benefit of faster reads and writes. And to take it a step further, with option 3, we can selectively query a set of line items based off of whatever filter conditions we decide. This is how to effectively optimize for compute over storage, because compute is honestly the bulk of the costs, and storage is and has continued to be more and more commoditized over time. Now, a lot of relational users might be hearing this and thinking, well, couldn't we just normalize the data in Cosmos DB and then do a follow-up query to get around this whole issue of denormalization? The answer to that question is absolutely yes. As we do that, one of the high-level themes you're going to find here is that when you normalize data, what you're effectively doing is optimizing for writes. The big drawback for duplicating parents is if I, let's say, as an example, frequently change the insurer or whoever the provider is on my patient claims. Well, I get that's unlikely. Let's stick with me here for the hypothetical. If I'm designing a data model that does frequently update metadata in the parent, what ends up happening is you have to update that parent object multiple times for each duplicated parent. And so one of the things you need to look at here is normalizing has some benefits if you're optimizing for updates, because the lack of duplicates means it's easier to do so by avoiding the fan-out update. Now, because we are not doing cross products across the database by denormalizing, you can grab all the information within the scope of a single query, making updates very cheap as a counterpoint. So what is the impact of normalization, denormalization on how developers want to think about their data model in Cosmos DB? Number one is, of course, to keep in mind that the goal when using NoSQL is to optimize for compute over storage. Compute is going to be the dominant cost in any modern cloud system. So it's honestly a much smarter thing to optimize around compute than storage. Optimizing for compute means you don't need to understand the data access patterns. Rather than starting with a set of entities and then thinking about the relationships, what you're really going to do is you're going to think about how data typically gets read and written. When working with flexible schema, as you remember if you tuned into the last episode on partition strategy, the first thing we're always going to recommend you do is figure out your ratio of reads to writes. If you have something that performs, let's say, 10 times as many reads over writes, you likely want to bias towards optimizing for the reads. And likewise, if you have the reverse, then it makes sense to optimize for the writes. Optimize for the aggregate workload. But of course, if you're going to have to make trade-offs, don't sacrifice the performance or cost of, let's say, 90% by optimizing for the 10%. If the opposite is true and you have more writes than reads, the main thing you want to pay attention to, of course, is update patterns. A tiny insert is going to be less expensive than a much more expansive update, and that's something you should always keep in mind. Okay, so we've gone through schema design around normalizing and denormalizing. We've talked about rigid and flexible schema. Before we dive into actually getting data into Cosmos DB, let's go through a couple tips for getting the hang of this concept of database design that comes with NoSQL. The first tip we'd give is that you want to avoid doing follow-up reads or having to break up a query into multiple database reads. So if there are filter conditions you continuously query off of, those a lot of the times can be candidates for duplication across your documents. This way, rather than having to look up an insurer and then find many line items for a given insurer, duplicate that insurer in each document so you don't have to look everywhere. Data that's written together often belongs together. Data that's not rendering together should be separated out into separate records. That way, when growing in a single giant record, the basic building block or unit grows. Another tip we typically give is to segment data by frequency of reads as well as mutability. And so what we mean here is how often the document mutates or changes, and what you'll find is there are certain properties that change with high frequency and certain properties that do not change with high frequency. An example for this would be, let's say, a different use case, which is building our product backlog. When I look at a product catalog, the quantity you have in inventory is going to change much more than the item's title, picture, or description. And so by separating these things out, what you can do is actually optimize for both reads and writes by having a data model that aggregates a lot of the frequently read properties that are read together. Now, the third tip is it's much cheaper and easier to think about the first two tips up front than to optimize this after you've built your application. Once you've settled on a data model, your objects will often look the same throughout the application as well as the business logic. So it's easier to plan out what these things will look like in advance. All right, so that concludes the fourth episode about schema design, normalization, and denormalization in Cosmos DB. I hope you enjoyed going through some of the day one things to think about, and tune into the next episode where we'll talk about getting data into your database with Azure Data Factory.